Welcome. This is Bill Foote, and this is Business Analytics 227. And this is the final review for the spring semester of 2023. What I'm going to show you are summaries of solutions to the two problems that I posed here in the Business Analytics 227 final review form. This is a reliably accurate way that the final will actually look. 3 questions. The first 2 have multiple parts. All parts must be answered for full credit in 2 places. 1, on this form, and 2, by taking an image of your notebook. Let me show you that. Let's see, get over here. All right, doesn't want me to, there we go. Now I can share my screen with you to show you what I am talking about. And this is the screen. This is the form. And as I just said, 3 questions. And the first 2 have 2 parts. I put points next to each one to show you their relative importance. And again, each question must be answered for full credit. Okay. Put all the relevant information here. Here's the first one. At the bottom of this, it will have a figure, in this case, a plot and associated table. The table, of course, is partially complete. You're asked basically to complete the table. In this case, for a 97% interval. Oh gosh, we use other ones, of course. That's where you're going to put your long answer text. You're going to upload an image to your notebook so that I can verify that you have been writing your materials in a notebook. That's your book. And the second question is very similar to the first. And we're still thinking here about spread risk. We run a different simulation. There will be a different picture here that I will insert. You will see what that picture is in a couple of minutes. Okay, upload an image. What are the 4 intermediate operations you will perform in order with the data on in Excel? This has to do with what? Named ranges, right? Named ranges. We can filter, we can format, we can document with formula text. All the things that we at least need to do. And there's a lot more, but that's a good start. A fifth one might be to go and get the data dictionary out of formulas so that nothing is left to the imagination of anybody looking through your excellent work. And then you attest and you affix. Those are the pieces. Let's go to the first question. There we go. So the first question talks about the spread, the difference between 2 prices, unleaded gas prices and West Texas Intermediate crude prices. And this is called the crack spread, as I explained. There's also spark spread for electricity. There's also the crush spread for soybeans into soy oil and meal. Lots of different types of spreads. Most businesses run on these spreads because they fairly well represent the process of input, some kind of processing. I mean, it could just be sorting the mail, sorting boxes in a warehouse, and an output. There's always a customer at the other side, internal to the organization or external, or both. And here we're looking at the riskiness of the spread. That's what we're studying here. We're asking the question and we're measuring an answer to that question, provisional answer, with standard deviations of the spread. we have a panel. The panel is actually to the left. It uses a minimum standard deviation of $2 per barrel and maximum of 10, sampling 12 observations using a uniform distribution. And all the statistics, and you will label your report with US dollars per barrel. These are all barrel equivalent. Now, there are two aspects to this report, A and B. Report the probable credible 97% range or interval of spread risk. And the first thing you're going to do is you're going to refer to the, there we go, refer to this diagram where we have chosen the mean spread risk. It comes from data to the min crack and the max crack variables, 2 and 10, which are standard deviations here, low risk and high risk. They're widths of how the min and the max can move across this crack spread that we have up here. One of the first things we notice, because we have a uniform distribution in mind here, which is what we're simulating from, is the population that we're simulating from is a uniform distribution. And let's see if I do this and that. Where the probability is 1 over B minus A. So everything's equally probable from a minimum here of A equals 2 to a maximum of B equals max. That's the uniform distribution. And in the Stats 2 book, there is a derivation of the standard deviation. Now, the mean is pretty straightforward. Common sense tells you, and common sense can reveal to you what this is. It's simply the middle and the median, mean and the median, and it's 10 plus 2 divided by 2. Too hard. B plus A over 2. And we know what the number is. It's going to be 6. The probability is 1/8 of each one of these. And when we use all of these facts, we can calculate the population standard deviation as B minus A divided by the square root of 12. Why is it 12? Well, that is a factor of integration. It's not the sample size, it's a factor of integration, and you can point this out in your report. This, of course, in this case, will be equal to 8, the range, divided by square root of 12, which is roughly, what, 3.41, and it's exactly equal to 2.31 US dollars per barrel, upper or lower case per barrel. So that's the start of it all. We run the simulation by sampling each of these, see what this is, between the indirect of D20 and so on, but the one that we're looking at right now is the crack. That's what we want. That's what we're going to be looking at. We want the mean, crack, in this case, risk. Notice it's quite a bit different in dimension and size from any kind of difference between WTI and UNL unleaded, and that helps us understand principally standard deviation. Okay, that's the idea of the range. Notice we're naming ranges, we're using formatting and formula text. And we're also using one more thing. If you want to mention it, there's the A and the A plus. Indirect allows us to point to a name that's in a label right now. And if it's in the name directory in formulas, it's in this name directory, which it is. There's the crack right here. It shows you where it is. There should be documentation here, but there isn't. It will use this array to perform all of the statistics. Okay, that's the idea. Whatever that array is, where's G20? Indirect G20? It's actually over here in the min and the max. Okay, so we do that. We set up an EDA, exploratory data analysis, which is containing all of the formulas we need, and all of the formulas are completely documented here. Without explanation, so maybe they're not quite completely right. And then we create a grid and midpoint frequency. We compare the Gaussian cumulative distribution function with the cumulative relative frequency that we have sampled. Here's an exact result. Remember what true is in the norm.dist means the cumulative. False would mean you've got it. Probability mass function that we discussed. Again, more documentation. Setups down here. So one of the things you could say, I'm only going to ask for 4, but a 5th one is modular tasks are kept in separate worksheets. And this is a good example of it. Lots of stuff going on here. Yes, it's all set up for the different pieces of our design in the dashboard of UNLWTI crack. All of this is set up for all of this, for this. Look, there we go. See that? This, all of those vertical lines and all the squiggly lines. So get back to verify the correspondence between the simulated credible interval. So we simulated this. This is a 97% credible interval. All of the probability mass in between these, the blue, in between the lower and the upper bounds, and those are cumulative probabilities. So you can just as easily use the ogive to get these as well, which is in fact what is happening here. In the EDA, there we go. It's a percentile, and that is a cumulative probability of 1.5% of all of the things that we simulated with mean crack. Okay, that's actually the crack risk in this particular case. So we repurposed the model. Okay, we've done the simulation. It works. Now this is the rest of the story. This is A. This is what you can put into your model, but what you have to describe, verify the correspondence between the simulated credible interval and the Gaussian lower and upper bounds for the 97%. The answer to that question will be the following. We're looking for the probability, lower bound less than or equal to the true value of the mean of the risk. Yes, you can have means of standard deviation. A little bit confusing. but not to an analyst. Such that probability is 0.97, and you might even mention that these are the a remnant of the number of ways in which that mean can occur between the upper and lower bounds. The number of ways in which the data is consistent with our hypotheses, which are between those lower and upper bounds. So we have hypotheses, remember, on the horizontal axis all the time. And we want to know which ones are better than the others. Well, here we're looking at the range, and that's the probability. And then if we do this, and we say that this is equal to the mean, that's the sample mean, minus a z-score, tells you how many standard deviations there are from the mean down to the lower bound, and then multiply this times the population standard deviation divided by the sample size. Now here our sample size, remember, is also 12. Don't get confused by that. How do we know that? Go to simulation, and we see that we picked 12. Okay, we happen to pick 12 for 12 months of the year, okay, whatever. That's how we did it. We could be a lot more savvy than that, but we're not. And that's the lower bound. Putting in the numbers, the formula up here has basically the same thing. Putting in the numbers, in our case, the mean, oh, it says it's 9. Don't want that. We didn't run the simulation. Oh, we better run the simulation. Da, 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 da. How do I know that's not the right number? Because 9 is too high. We know that, and here's the common sense that gets us in trouble on exams and in front of clients. Yeah. Yeah, and it ran. Thank goodness for that. There we go. Mean is just about 6. So you can take this as 6. I'm going to peek it there. There's all sorts of numerical reasons why that's the case. But let's just put in 6 here. Minus. Now, we had figured out that there are 2.17 standard deviations below at a 0.015%. So let's illustrate that before I put anything else up here. There's our blue curve. There are 2 red dotted dashed lines. Up to this point, we have 0.015. Here's the mean of 6. Here are all the possible mu's we could be thinking of. We can also draw, if we want, a z-score with a mean of 0. Remember what the z is. Value minus the mean divided by the standard deviation. So it's centered on 0 all the time. It always has a standard deviation of 1. It's per standard deviation. And this number down here ends up being minus 2.17 by symmetry. This is totally symmetric. This area equals that area. We get plus 2.17 over here. Our work's already done for us. And in Excel, where do we get those numbers? Look at your formula up here. The norm inverse, probability of the lower, which is 0.015, comma 0, comma 1. Those are the mean and standard deviation of the standardized normal, which works right in distribution. We're multiplying that times SD, and that's 0.74. We know that the crack spread population standard deviation is 2.31. Well, we can come awfully close here. Put this in red. 2.31 divided by square root of the sample size. And we're going to come up with a number that is awfully close. And that number is going to be 4.38, very close to the 4.42. And 1E6, now 1 million simulations might get us there. But it's kind of a rocky simulation. There are issues inside of that simulation. But we don't need to, because this is not an exact science. If we're off by a 32nd of an inch on a 100-foot long roof, yeah, we better be exact or that roof will warp. This part of it is not so difficult, because what's happening here is these are very approximate bounds that we have here. So please realize that. Okay. And now the upper bound is just going to be 6 plus whatever this number is. So we can write that here. Root of 12. And that will be equal to 7.6, which is, again, awfully close to the simulated numbers. So we know our simulation is close, and this is a good way to verify it. But this is also the back of the envelope that you can use if you truly believe everything is Gaussian. And we think that means and standard deviations are probably Gaussian. Why? Because they're sums. And they're taking sums of sums of sums. And the ones closest to the lower bound of the crack are less likely to occur, as well as the upper bound. Why? Because we're taking samples in between. Very unlikely that when we sample 12 times, we're going to get that lower bound or very near it, or the upper bound and very near it. And in fact, we don't. And that's what the distribution is. Okay, so this is what you report. Client wants to know what would be the impact of an increase in the simulation sample size from 12 to 30. Well, we have a way of showing that right here, right now, by changing that number and that number to 30. So you can show it this way. You can recompute this up here. Draw a box there, but come back to that. Oops, back. There we go. I can compute it here immediately. Instead of using SD, I could use the 2.31 divided by square root of 30. And that's why we get to use this massively complicated calculator. It means that, oh, look at that. Let me make sure this is the upper. Once you have a connection. at the final exam. So what happens? It narrows the range, narrows the range. So all that happens here on our diagram is we move from there to here. We have a narrower range of opportunity. Now, for people who invest in options, and anybody who has recourse in any kind of contract that invests in a house, for example, you invest in options. You don't have to be an options trader. We're all options trader from that point of view. This constrains your ability to fight change when change goes against you, and use change for your for yourself when it comes up. That's what risk really means here, not uncertainty in terms of true unpredictability, but like black swans, that kind of unpredictability. But in the volatility of this risk itself. Okay. Anyways, the bottom line here is for 2 points that it contracts it to. You need to report these two numbers, 5.07 and 6.91. So we go from one interval to another. You can label these intervals. You can even figure out what the new z-score is. Z-score is going to be this calculation. And that's 0, 1. That's that's this. Oh my gosh, it's the same z-score, isn't it? But the number of standard deviations is going to be different. I'm sorry, the number of standard deviations is going to be exactly the same, plus and minus that, because the probabilities don't change, but how they modify, we calculate this number times 2.31 divided by square root of 12, you get a different number. You get the number from before, or 30, we get an even different number. It's almost $1 per barrel down, whereas before it was, and this is what you can report, it's two numbers, at almost $1.50. So it's like, about 50 cents a barrel difference is how I would do this. Okay. And you can write these in here. You can show the contraction. But what happens is when you contract, you're using actually a different curve now. I did not show that. So that the new Z curve is still minus 2.7. What has happened is you squeezed it. Okay, so you could frame your story in any number of ways. Show your calculations by hand, and your story could be, well, when it's square root of 30, we tighten the distribution. So that's the red distribution here. Okay, so I'm going to leave it at that. That's the first one. Enjoy. Second one coming up. So in this one, this is directly out of the form. Client wants to know if the spread risk of $8 a barrel is a high or low risk. We resimulate the model in question run with a range of 5 to 13. Okay, let's go back and do that before we do anything else. And that means we go to data, 5, 13. Notice it's exactly the same population standard deviation because the range has not changed. Okay, simulation. Fortunately, it does not take that long. A million would. A million might mean you could get a cup of coffee out of the vending machine downstairs. Yeah, could take a while. This is only 10,000. Ah, there we go. And now we get these numbers. Oh, still working on the 30 there. Let's move that off. And okay, good. And now we have a different situation. The mean now is 9, which makes sense because it's halfway between 8 and 13. Equal number up and down. Okay, so remember, the whole thing is all about counting in the end. So we don't need to go too far afield from that basic idea of arithmetic and counting the numbers. Look at the peak on that. That's a plus. All right, so that blue one there. So we have 9 and 0.75 versus 6 and 0.75 as we go back and look at the hypothesis testing. So calculate the odds that a spread risk of 8, that's where we're going to put the spread risk in up here, 8. And we have a low mu, we have a sigma of 0.75. Let's put that in there. That 0.75. Yep. But you can see down below that what happened is low and high markets are not low risk, high risk in the sense of the riskiness. See, this is about risk. The mu is the mu of risk. Okay, just to put a point on it. And this is a target risk. That's our target risk. Also put it in here for our own benefit, dollars per barrel. Okay, just to make sure that everybody knows what everybody else is doing. Okay, and the low one, remember, was 6, and we just found out that the high one is 9. Okay. So we got that, and you can see there's some overlap down here as well. There's quite a bit of overlap, but we want to ask: is this a high or a low risk environment measured by average risks, which themselves have a riskiness of 0.75? But don't worry about that. That's called kurtosis. You don't need to worry about that, although you can put that in. And if we go through our complete discussion on this, we have we calculate a likelihood function here of that 8 occurring in the blue with a 6 and a 7.5 configuration of mean and standard deviation. False for the probability mass calculation. So we're getting actually a point wherever 8 is, and I did not put this here in the setup, but I think it's right there. I think that's 8. There we go. So I do have it there. So it's right there. Is that a high risk or a low risk? Well, we have 2 ways of doing that, and in this particular case, it's very clearly very clearly. A low risk. No, it's very clearly a high risk. Can you see it though? 14 times higher than the low situation. But so we calculate this, multiply it times our probability of an hypothesis. And here we're saying that low and high risk situations are equally likely. And here's the joint probability, 0.076. You can see right now that there's very clear indication that between the two joint probabilities, the high is more likely. And we add these up to get 0.1169. We then use that to normalize the joint probability, normalize it. You see G4 is the numerator, G6 is the denominator. These will, of course, add up to 1. When we do all of that, compute odds ratios. 93 divided by 0.06 will give you 14 times, 14, 15 times. Okay. The same story is down here in terms of the overlap. I'm not asking you for that. It's not, that is a bonus for those of you who are going to be going on and using, all of you, I think, using this material where the sigma to the left, 0.75, 0.75, might not be the same. And I think in class we showed that they were not the same and we might have different results. So we need to use that lower probability of a tail being greater than the alternative. The low situation, the high, more density there than in the low at 8, roughly. Magic of the fingers here. There we go. And if we start drawing something in here, which is a very dangerous thing to do. Right there is where 8 is. See that there's not much in that blue, and there's a lot more in the orange. Okay, common sense tells you, but I think common sense also tells you that it's not quite clear. Why is it not quite clear? Well, 9 is as far away is 4 units away from 13, and 4 units away from 5. It's max and min. 6 is 4 units away from its and 4 units away from its low. So an 8 is closer to the 9 than it is to the 6 in that sense. In what sense? In the probability sense. So it is only one. And do we need probability? Maybe not. But you can, again, the whole point of this is to show that the probability gives us the right answer from a common sense point of view. 8 is 1 unit away from 9, but it's 2 units away from the low of 6. So it's closer to the 9. And we have a principled way of finding out logically, given this data, 8, consistent with all of the rest of our assumptions, logically, the 14 is logically larger and arithmetic logic than the 0.069. And it's the one we would check off. We would prepare for a high risk environment if this were set alongside a decision. So what do you show? In your notebook, you can show the calculations, this calculation and this calculation. You can say, for example, in your notebook, as an example calculation, over here, in your notebook, that the probability of seeing 8 given 8, 6, and a, we can do it like this, a 6 and a 0.75 times probability of 8 of 6 occurring, the hypothesis is equal to the probability. The hypothesis 6 and the data 8. Remember the wedge from the beginning of the course means and, both and. And we find that it's equal to 0.152. We similarly can write probability of 8 in the presence of a higher risk, 9, spread out 0.75 again. Again, it's the probability that we see nine. And this is equivalent to the probability of 9 or 8. This is where the consistency comes in. It's 9 and 8. When consistency means they're together. If they're not very together, they look more like an or, but not an or. They're still an and. It's still an and. That hypothesis of 9 and that data of 8 are colliding. They're mashing here. And we find that this is much bigger. 2187. Again, these are not exact in that sense. They're relatively bigger and smaller. That's 87. You can put in the numbers here for that. Oh, actually, that's not true. That's 01. I don't get my full points here. Do I? That is 0 point, right? So that's not true. Is it? No, that's 1015, 105. Okay. Now, what is true? Watch it when you do these things. 0.0076 is the correct number. Oh, okay. Ahead of myself, as you will too on your exam. But now you know not to. Oops. I got that correct. Yep. The other one is 1093. And now we can add those two numbers up in order to grab at their relative contribution. And once we do that, I think that's 11. Oops, I don't know what 11 something. 1169. 1169 is the number, though. Sometimes the pen is mightier than the sword. Not working. Really having a conniption with me right now. So it is 1169. So we can see the whole thing. 1169. Then we take each one of those in the calculation. That divided by 1169. 7 divided by this. 1169 and 1093, the joint probability of data 8, and this 9 height and 7.5 hypothesis, and we get 93. We can calculate 93 divided by 6 and get roughly 15 times. So that takes care of all the calculations that you need to show. Provide an interpretation for 2 points. For 2 points, this is the layup. The layup is that it's the calculation of the odds and its interpretation. It basically says that with common sense, we think that 9 is closer to the target risk of 8. Yes, and it is. Okay. But in probability, it means it's 15 times as likely as being close to 6. Likely, more likely, it is close to 9, but it's 15 times. So managers are calculating odds of one project versus another, one investment versus another, one way of managing resources versus another. They're going to rank them in priority order, and one of the priorities they're going to consider is this odds ratio, is the odds ratio, and that's what they would consider here, 15 times. So you got your 2 points with all of that. Okay, so again, this is a summary, and I'm amazed at the thing, technological triumph of, yeah, it does work. Ah, there we go. That's the rest of the story. And we get use that 0 point. Okay. No, that's 93. I'm just copying stuff, and that's very bad. But we'll do it again. 0.93. Well, there you have it. All of this will be together in one place so that you can have the final review sheet. It has everything in it you need to be successful on the final exam. As an example, of course, the final will not be these numbers, probably nearly everything else. And there we go for your online final exam. I will stop the share, stop the madness, and get you back to another wonderful. Well, your weekend is a reading weekend, and I hope this helps. I will be posting this very shortly. Thanks once again for the opportunity to be working with you all semester. It has been a pleasure. And you don't need any luck. The odds are in your favor. Take care.